We are back and we are into CPU Architecture 2. I'm not sure what we're going to do here, but let us find out. I guess we'll start with XOR again. XOR again. Using the instructions of your computer, read the input twice and XOR the two values together. Okay, more programming. Okay, so I think this should work. I'm basically creating A and B, and then not A and not B, ANDing A and not B, ANDing not A and B, and then ORing those together and sending it to the output. I think that should work. Let's try. Nope. There we go. Okay, so now we created XOR just from software. All right, let's do Byte Constant. Create a circuit that always outputs the number 164. Okay, I think we can just do a byte splitter to an on. Is that going to work? Only puts out the first one. Okay, well, we can do it a different way, kind of a simpler way maybe. So we definitely going to need that. Right, so that just gives us, oh, then we need a maker. Okay, 128. And then what do we need? $160, and then we just need one more for a 4. Okay, this should always output 164. All right, Byte XOR or equality next. Output green when both inputs are the same. Okay, so we're going to split these out, and we're just going to check. There we go. So pretty simple actually. We're checking each bit individually and seeing if they're matching with this XOR gate. If they're both green, it'll be green. If they're both red, it'll be green. But if they're different values, then it'll be red. And then so we're checking for each bit, and then we're ANDing all those together. So if they're not equal, then it'll be red, and if they are equal, it'll be green. Let's try it. There we go. Not too bad. Okay, Byte XOR is next. Create a circuit that XORs 2 bytes bitwise. Okay, shouldn't be too hard. We can just split these out. It really is just a very straightforward, simple way of doing it, and it should work. So let's do it the straightforward, simple way rather than the clever way that maybe uses less parts. Yeah, we'll just go with that. Try it out. All right, easy. Okay, next up, unsigned less and signed less. Let's start with unsigned less. Create a circuit that outputs green when the first input is less than the second. Interpret the bytes as being unsigned. Okay, so I should just be able to add this one, and then we will not this one. Okay, so I think I just need to add it to the carry, not the last bit here, but the carry. And I think this should work. There we go. Just using a bit of subtraction to figure this out. Unsigned Less. This might be easier. Create a circuit that outputs green when the first input is less than the second interpret the bytes being signed. Now, I think this should work pretty much the same way. Okay, and for signed less, I just basically exactly replicated what I have for the unsigned less. And let's see if this works. No, it does not work. Okay, I'm not entirely sure if this abomination will work. I think I've covered all my bases. Maybe I'm missing something. Let's try it. Oh, this should be a triple and... And we should add in this guy. Let's try it again. There we go. So basically I've just accounted for whether these are both negative, both positive, one negative, or equal, and kind of broken down the logic based on that. This looks really messy because it is, but it seems to work. Okay, up next is wide instructions. Create a device that saves the program output on even ticks and outputs both bytes on odd ticks. Okay, so we want to register. There you go. That should work. Alright, so this is not too bad. Just basically like a little flip-flop with one register, one switch, and then just a counter. Finally, it's time for you to start building the leg architecture. The leg architecture is a computer that takes 4 bytes per tick from the program. The first byte describes the operation. Since many operations take 2 arguments, like add, or, etc., the second and third byte are for arguments. And since most operations return one result, the fourth byte is for the results. Okay, so what do you have to do? Click the schematic icon and create a new empty architecture. New schematic. Leg. Is it 1G or 2? I can't remember. Place a program block with 4 outputs. Okay. Place a counter, set its increment to 4, and connect it to the program block. Okay. And connect it. Okay. Add 6 registers. Click Edit Link Components on the program component and connect registers 0 to 5. Connect the counter to 6 and the output to 7. And the output to 7. Finally, in this level, the opcode is always 0. That means we add argument 1 and argument 2 and save the results to the destination. The value of an argument or destination refers to one of these places. Okay. Okay, I think this should work. This ended up being a lot more complicated than I thought it would be, and I've maybe made it too cramped. But I think I have everything hooked up right. So let's try. No. Register 4 should have a value of 104. So did I hook up something wrong? Oh, I did not hook it up right. Okay, then I think this should work. Let's try. All right. Just kind of annoying, and I made a mess of it when I probably shouldn't have. We started our new CPU. It looks messy. Okay, opcodes. I'll be honest, I'm kind of dreading doing this because I don't want to hook all this stuff up, but hopefully it goes fast. Implement the following opcodes. Add, which you've already done, sub and or not XOR. The opcode not ignores the second argument. Right now we're just assuming add for everyone, but we got to actually break this bit out, and let's find a spot for it. Maybe we just do it up here where we have room. I think this might work. Yeah, I think this might actually work. Did I do the sub right? That's my only question. Let's just test it out and see if this all works. All right, that was not nearly as bad as I thought it was going to be. Immediate values. Sometimes it is useful to load a value directly from the program instead of from registers. This is called loading an immediate value. In the leg architecture, we signal when we want to do this in the opcode. We can do that in the following way. When the 8th bit of the opcode is green, use argument 1 as an immediate value instead of as registers. When the 7th bit of the opcode is green, use argument 2 as an immediate value. Okay, so we're looking at these two bits right here. I think probably a multiplexer is going to do the trick here. Okay, I think that should do it. No. Oh, I have these swapped. 8th and 7th, not 7th and 8th. So actually this is a simple fix. And then I think that'll fix it. Let's try. All right. Okay, final level of CPU architecture 2, adding in conditionals. Fun. Add if statements to your circuit. For the if statements, the two arguments are compared, and if the condition is true, the counter is set to the jump address. The previous instructions had the 4 bytes to represent opcode, argument 1, argument 2, result. For if statements, the bytes represent opcode, argument 1, argument 2, and jump address. In addition to the previous opcodes, add 32 if equal, 33 if not equal, 34 if less, 35 if less or equal, 36 if greater, 37 if greater or equal. Use unsigned for the comparisons. Each opcode does what their name implies. Okay. So where's my program counter? Right there. Okay, so this should be all of them. Equal, not equal, less than or equal, greater than or equal. And you can see it's like the way the logic works, it's like greater than or equal is basically not less than, because we don't have a greater than component, but that works. So this should work, but we also need the right jump command to be set. I don't really remember what this switch is for, if I'm being honest. What did I do? Short circuit here. Yeah, so this switch is causing a problem now. Will this work? Ooh, it might. Alright, let's try. At least no short circuit. Just another issue. If less than or equal. Okay, so my if less than or equal is busted. Oh, this isn't connected. That's why. All these little connections, sometimes you just don't make them. Or a lot of times you just don't make the connections correctly. And that breaks things. All right, let's try again. Congratulations, you finished the leg computer. All right, we did it. I will show you some upgrades you can make on the path to implementing functional calls, but from here on, the details are up to you. I won't tell you what opcodes to use and so on. All right, cool. Well, that's CPU architecture done. I guess the leg component is done. But next up is functions and then assembly challenges, and then we're done. So man, yeah, we've done a lot. We've come a long way. I will see you guys next time.